Hello there, 8th graders. This is Mrs. Minowitz, and I'm here today to talk to you about motions of the Earth and also about the seasons. So the first motion that we're going to talk about is called rotation. And rotation is the spinning motion of an object on its axis. So in something like, think like a top spinning. This is what causes day and night on Earth. And the period of rotation is the time it takes for something to rotate once. Many objects in space rotate. Stars, the sun, planets, Earth, the moon, all rotate. This takes 23 hours and 56 minutes, or 1 day on Earth, and that's how we get a day and night. Another motion that we're going to talk about here is revolution. Revolution is the motion of an object around another object in space. So this time we're moving around something else. Planets orbit their stars. Okay? Moons orbit or revolve around their planets. The period of revolution is the time it takes for one revolution. The further that you get away from something, for example, as you get out further than, say, Earth, say you were Mars, it's going to take you longer to go around the sun than it would, say, Earth. On Earth, this takes 365 days, 6 hours, and 9 minutes, or 1 year, to go around the sun once. That leads us into this idea of what's called a leap year. So how often do we experience a leap year and why? If you think back and you think through it, it is 4 years. And the reason why we have a leap year every 4 years is because there are 6 hours left over each year. If you look back here, we have an extra 6 hours. Well, over 4 years, that's going to build up into an extra day. So we add that onto the calendar to kind of balance it out because it's not an exact number of days that takes a year. So over time, we kind of balance things out in the calendar. Another thing that we need to talk about here is what is called orbit. Orbit is the elliptical path an object takes as it travels around another object in space. Elliptical just means like an oval. Okay, so orbits are not perfectly circular. They are slightly, or to varying degrees, more oval shaped. And it is often shown by an arc here, or this line, showing the path that something takes. Okay, that is an orbit. So if we look at this diagram here, this is showing each of those 3 words. A here is showing rotation, something spinning on its axis. B here, that arrow, is showing that moving around something else. That is called revolution. And C is pointing to that path that something is taking around something else, so that is called orbit. Okay. Sometimes students confuse revolution and orbit. Revolution is the movement or the motion, and orbit is the path. Okay. This brings us to another concept called orbital eccentricity. And basically, orbital eccentricity is a parameter that determines the amount by which the orbit around another body deviates from a perfect circle. So in other words, how much of a circle is this, or how much of an oval is this? So a value of 0 is circular, and values between 0 and 1 form an elliptical orbit. So if you look at the diagram below, 0, circle. When you get close to 1 here, we have this very long stretched out oval. And to put this into perspective, the orbital eccentricity of the Earth is 0.017. So very, very close to a circle, but it is not a perfect circle. It is slightly elliptical. Okay. All right. So our next topic here is seasons. So my question for you is that the Earth is closest to the sun in January. Why then is January typically the coldest month in the northern hemisphere? And if you've thought on that, and the reasoning behind it is because the distance between the Earth and the sun has really nothing to do with the seasons. The distance between the Earth and the sun changes very little throughout the year, so that it doesn't really play an impact on the seasons. And the reason why January is the coldest is because that is when the northern hemisphere is tilted away from the sun. Which is what causes it to be cold then. So there are 2 reasons why we have seasons on Earth. The first reason is that the Earth is tilted on its axis. It does not, right, it looks kind of over in here in this picture. It is tilted at about 23.5 degrees. And we'll talk more about that, how that causes seasons in a minute. And the other reason why there are seasons on Earth is because we get heat in the form of radiation from the sun, which warms things up to varying degrees depending on things like the tilt. What happens with tilt is that in the summer, We get more concentrated rays of sun than we do in the winter. We also get more hours of light in the summer than we do in the winter. Days are longer, or which day is really the same amount of time, but the hours of daylight that we get is more in the summer than what it is in the winter. If we put those things together, this is what causes higher temperatures in the summer. So this drawing here kind of shows you what happens with the different, because of the tilt. So in the winter, we get these rays of sun are more spread out. It can't heat as much of an area because it's more indirect. In the summer, the sunlight is more direct. It is closer to the same area, and it's able to warm more because of that. A couple other words or things that we need to go through are the words solstice and equinox. So solstice is either of the 2 times a year when the sun is at its greatest distance from the celestial equator. That's basically saying when we get our longest days and our shortest days. And this happens in the winter. The winter solstice for the northern hemisphere, which is where you live, happens, depending on the year, in about December 21st or 22nd. This is when we would have what's called the shortest day of the year, when we have the fewest hours of daylight. Okay. In summer, we have the summer solstice, June 20th to 22nd, depending on the year. And this is when, in the northern hemisphere, we would have the longest days or the most hours of sunlight because of how the Earth is oriented. The other word that we want to talk about here is equinox. So equinox is when we get a equal length of day, equinox, equal, and this happens in both the spring and the fall, and this would happen in both September and March, and this is when days are approximately, day and night is approximately of equal length all throughout the Earth. All right, so those are the words solstice and equinox. Sometimes students get them confused, but if you remember that equinox is equal, you should do just fine. All right, the other thing we're going to talk about here is we're going to look at a simulation looking at what happens with seasons. We can do some things on a simulation that we can't do in the real world. So one of the things we're going to look at is what would happen to the seasons if the Earth was tilted 0 degrees on its axis. So I have this simulation here that's showing the Earth going around the sun. Obviously not to scale here, but then down here we're showing the temperature and how the seasons are changing. And right now it's set up to show what is happening on a regular daily basis. Nothing has been changed here. Okay, and we can see the seasons changing. It gets warm, July, August. It gets cool, January, February, just like what we would expect. But if we change our axis tilt to 0, and we click OK, and then we look at what happens. Okay, we speed this around here. And we're going around, and if you look at both the top and the bottom, you will see that we don't really get seasons anymore. We don't have that difference in temperature. So for here, you could say that it would be the same season all year because there wouldn't be a tilt to cause that differences in how much, how direct the sunlight is. So we'd get the same season all year. Okay. All right, it wouldn't get really hot in the summer, really cold in the winter. It'd be approximately the same temperature all year. All right, another thing we want to look at is if we're looking at the same idea here, what's going to happen if instead we change the tilt to 90 degrees, which is basically putting the Earth on its side, which is very similar to the planet Uranus. And if we start that and we look here at the temperatures, okay, we watch that go around once. Now if we look here at the bottom, our temperature graph, we're going to see in the winter it gets very, very cold. And up here in the summer, we're looking at like deadly temperatures. So if the Earth was tilted more than its standard 23.5 degrees, it is going to have more extreme seasons. Okay, so if it was tilted more, okay, we would get more extreme seasons. It would be hotter in the summer, and it would be colder in the winter. More extreme seasons. All right, the third question that I have for you, and we're going to look at, is what would happen if we change the eccentricity of Earth, and if it had a more eccentric or more oval-like orbit, what would happen? So if we first change our tilt back to normal, and then we go through and we change our eccentricity, change orbital shape, and instead of it being 0.017, we put 0.5, and then we look at what happens here. Okay. And there's not one really there's not one really basic answer for what's happening here. If you're looking at this, some areas of the globe would get way too hot. Certain areas, they get really cold when we got really far away. So in this circumstance, if we had a really eccentric orbit, the distance between the Earth and the Sun would have a much larger impact on the seasons, when right now it has essentially no impact. We will talk more about seasons and about motions of the Earth in class. Thanks.